Hello students, welcome to my channel. Today we are going to discuss a very interesting topic that is called pure rolling. So this is you will be studying this concept in the rotational mechanics. It is little bit concept, so I wanted to explain it very in simpler form. Let's try to understand what is the pure rolling. Pure rolling, when we say the pure rolling means a object, suppose this disc is rotating on this plane surface. It has got two motions. Primarily, has two motion. One is the translation motion, means center of mass is moving at a certain velocity in a linear, this yellow direction, in the linear motion, but its outer point is rotating at the omega angular speed of the omega, and it has got other motion, that is pure rotation. When these two combine, then we observe there is a pure rolling. The condition of the pure rolling, that this point should not slip on the surface. So this is one of the precondition of the pure rolling. Suppose a car is in the slippery road and the wheel is rotating and it's slipping on the road. So it won't be the pure rolling until unless that caught friction and the wheel is not slipping on the road and the car is traveling at the linear velocity and the tire is rotating at the angular speed omega, then it is the pure rolling. The tire is under the pure rolling until unless it's not slipping on the bottom surface. So if you look at this diagram, this blue diagram, if you look at the outer point of this circle, this point is moving in a cycloid fashion. Means this point is going down, then it is going up. If you watch this carefully and take the videography of this point, it moves in the cycloid motion. Whereas the center of mass is moving in the straight line. This yellow is the showing the straight line. So VCEM is the center of mass velocity. This CM is the center of mass and V is the velocity of center of mass. So VCM is in the linear motion, whereas this outer side is moving in the cycloid type of motion. So there is a relationship exists between the VCM and the omega. That relationship is the VCM is equal to R into omega when there is no slipping. This equation exists. VCM is equal to R into omega, where R is what? R is the radius of this disc and the omega is the angular motion of this disc. So this exists when there is no slipping. So we understood. So this is the pure translation. It means all the point is moving. This circle is moving like this. So VCM is moving at the velocity. Every point is moving with the velocity VCM. Whereas the pure rotation, this is fixed and this is the axis, Z axis, and this is rotating at this axis. Means this is pure rotation, and this every point is rotating with the omega angular speed omega. So this is the pure rotation. When we combine these two motions, then it becomes pure rolling. Now after combination, what happens? This center of mass is here at the stationary. So center of mass, if you add it, VCM plus V is equal to 0. This means the center of mass remained with the linear motion VCM. If you observe in this pure rotation, this center of mass is not rotating because it's at the center is not rotating, so it will not have any angular speed. This omega will be 0 at this center of mass. The center of mass will only be moving with the linear velocity VCM. Whereas look at the other point, look at this point, bottom point, look at this point. This is VCM in this direction. All points are moving with this VCM, whereas this R into omega, this R into omega is equal to VCM. So this, if you look this point, VCM is in the opposite direction and this is VCM in this direction because it's rotating. If you observe it, this had got tangential velocity in this direction, VCM in this direction, whereas it is in this direction. If you add it, VCM in this direction and VCM is in the opposite direction, if you add it, then this V is equal to 0. Why so? Because these had got opposite direction. So this is as the instantaneous rest position. this bottom of the tire, bottom of the disc is at the instantaneous rest position. This point is at v is equal to 0. But it will have the angular speed. But v is equal to linear will be 0. Whereas look at the top point. This is moving v cm also. Because of the rotational motion, this will have this in this direction, and this is pure translation is also having this direction at the top of this. If you add it VCM plus VCM, it will become V is equal to VCM plus R into omega. That R into omega is nothing but VCM. So V is equal to 2 VCM. So this top point, it has got twice of the velocity of the linear velocity of the center of mass. VCM is the center of mass linear velocity. This top point, it has 2 VCM. So very important concept. If you look at this pure rolling, this will rotating at the omega, whereas this is at the instantaneous rest. This center is at the linear velocity VCM, and this top point is V is equal to 2 VCM, means twice of the center of velocity of the mass. Now look, what is the, if somebody asks what is the total kinetic energy of this disc if it's in the pure rolling. So when it's in the pure rolling, it has got two motion, translation and rotation. Due to translation, it will have the kinetic energy, we know that half mv square cm. Whereas with the pure rotation, we have rotation, we also know half ICM omega square, where ICM is nothing but the moment of inertia at this axis, z axis, about this z axis, where omega is equal to VCM. This is the total kinetic energy. It's a sum of pure translational kinetic energy and the pure rotational energy. So it is represented, total energy is equal to half ICM square plus half mv squared cm. So this is one of the topic I wanted to discuss. Let's understand a simpler question I am going to explain. Suppose an object is, this is the triangular prism, and this is a sphere is at the position here, and when it falls here, somebody asks what will the kinetic energy when it reaches to the, this is point A, this is point B. When it starts rolling, this is under pure rolling, means it has the rolling like this, and it is going in this slope with the linear velocity. So somebody can ask what is the kinetic energy when it reaches to the point B. So we initially this has having the potential energy is equal to, because this height is z, we know that potential energy is equal to mgh. This mgh will be gets converted when it reaches to this point into kinetic energy. And kinetic energy will have two components here. One due to linear motion, that is I already explained half mv squared cm, and other due to the rotational, it will have the kinetic energy half ICM omega square. So and if you want to calculate if for a sphere, we know that ICM is equal to sphere, this is sphere, and this will be the 2 by 5 mr square. If you put this equation where omega, we know that VCM divided by R, if you put these two in this equation, what will happen? Half m plus I means 2 by 5 mr square into omega means v square c m divided by omega r square. So this will go. So if you calculate this, half m plus one by 5 m c square. So this will, if you calculate, this will be 7 by 10 right? Seven by 10 half MV square. So if somebody is asking this find the velocity when it reaches to the point B, this is the equation we observe it. M cancel out, means V square CM is equal to 10 by 7 GH, means VCM is equal to root under 10 by 7 GH. So it means when it reaches here, this VCM is equal to root under 10 by 7 GH. When it is a sphere, so this will be this point, this 10 by 7 is the component, depends on the moment of inertia of the object, but it's not depending on the mass and radius. Very interesting point. The VCM is not dependent on mass and radius of this object. Only it is dependent on the factor which comes out due to this ICM, moment of inertia. If it's this, it will be different factor. It will be hollow sphere, it will be different factor. If it's cylindrical, it will be different factor. So this 10 by 7 is dependent on the moment of inertia of this Z axis. But VCM is not dependent on mass and radius of object. That's very interesting. It's dependent on the factor due to moment of inertia. So I hope I explained this becomes a little bit complex in the rotation because it has two motion at a time. So we need to understand independently two motion, and we can summarize the pure rolling. We can understand the pure rolling in a complex situation also. I hope you like my video. Please subscribe my channel. Thank you.